Hello everyone, welcome back. This is part 3 for the chemical bonding series of grade 11 chemistry, the Ethiopian national curriculum. So on this video, we're going to focus on formation of ionic bonds, mainly 2 points. The first one being factors affecting the formation of ionic bonds. The second one being using the Hess law to calculate lattice energy of ionic bonds. In the last video, we've talked about ionic bonds. We've said that ionic bonds are bonds that are formed by complete transfer of electrons. Okay, they are electrostatic forces of attraction holding positive and negative ions together. A good example is sodium chloride. Sodium chloride has positively charged sodium ion and negatively charged chloride ion. The electrostatic force of attraction between these two ions will be our ionic bond. Let us talk about the factors affecting the formation of ionic bonds now. The first factor is ionization energy. So what is ionization energy? Ionization energy is the energy required for the removal of 1 mole of electrons from 1 mole of gaseous atom to form 1 mole of +1 charged gaseous ion. As you can see, 1 mole of sodium gas is losing 1 mole of electrons to form 1 mole of +1 charge. This is ionization energy, or the energy required to do this is called ionization energy. So how does ionization energy affect the formation of ionic bonds? Elements with low ionization energy favor the formation of ionic bonds. Okay, elements with low ionization energy favors the formation of ionic bonds. Why is this? Because elements with low ionization energy are most likely to lose their valence electron easily, making them a cation. Okay, the energy change for the removal, for the addition of 1 mole of electron into a neutral atom to form 1 mole of -1 charged gaseous ion is called electron affinity. This is a good example here, okay? So how does electron affinity affect the formation of ionic bonds? So elements with high electron affinity, favor the formation of ionic bonding. Okay, they favor the formation of ionic bonding. So elements with high electron affinity will be the halogens. The halogens have the most electron affinity. Okay, so they are more easier to form a negative ion, which will be one of the components in ionic bonding. Okay, so elements with high electron affinity favor the formation of ionic bonding. Now let's talk about the third factor, which is the lattice energy. So let's begin by defining what is lattice energy. So lattice energy is basically the energy released when 1 mole of ionic solid is formed from its ions in their gaseous states. When 1 mole of ionic solid is formed from its ions in their gaseous states, this is called lattice energy. Okay, so we were defining it as energy released. That is why the negative sign is here. Okay, this can also be defined the other way around. Lattice energy is also energy absorbed when 1 mole of ionic solid is dissociated into its respective ions in their gaseous states. Okay, this is positive here because energy is absorbed in this process. Okay, this is an endothermic process. This one is an exothermic process. So now let's talk about what factors affect the magnitude or the value of lattice energy. So lattice energy is directly proportional to the product of the two charges. Q1 stands for one of these charges, Q2 stands for one of these charges, okay? And then it is inversely proportional to R, which is the distance between the two ions. So what does this tell us? U is, or lattice energy is inversely proportional to the distance between the two ions, but directly proportional to the product of the charge of the two ions. So from this, we can conclude one thing. We can conclude that small ions with larger charge, small ions with larger charge will have high lattice energy. Okay. So how does lattice energy affect the formation of ionic bonds? Larger lattice energy favors the formation of ionic bonds. Okay, so let's summarize this. Low ionization energy, high electron affinity, and larger lattice energy favors the formation of ionic bonding. So now let's talk about calculating U, or the lattice energy. So lattice energy cannot be calculated directly using experiments, but we can determine it indirectly using the Hess law. So what does the Hess law say? Overall reactions enthalpy change is the sum of all enthalpy changes of the individual reactions that make the reaction up. Okay, what does this mean? If we have a reaction that can be done using 2, 3, 4 steps, the overall enthalpy change in H of the overall reaction, or we can say total enthalpy change, is the same as sum of enthalpy change in the first reaction, enthalpy change in the second reaction, enthalpy change in the third reaction, and so on. Okay, so this is the Hess law. So we're going to apply this concept or this law to calculate enthalpy change of ionic compounds indirectly. Okay, indirectly. Now let's look at the Born-Haber cycle. The Born-Haber cycle that we're going to use to calculate the lattice energy for sodium chloride. Okay, so as you can see in this reaction, sodium, 1 mole of sodium solid plus 1 mole of chlorine gas will react to give 1 mole of sodium chloride solid directly. This is called enthalpy change of formation. Okay, this is enthalpy change for the formation of 1 mole of sodium chloride solid from its constituent elements. This is the direct choice, but this is not always the case. 1 mole of sodium chloride solid can be formed in 5 steps. The first step being the conversion of sodium solid into sodium gas. Second step, chlorine molecule into chlorine atom. The third step, ionization of sodium. The fourth step, ionization of chlorine, and the reaction of these two to give sodium chloride. These are the 5 steps for the formation of sodium chloride solid, starting from these two elements. So according to Hess law, the energy required, or the enthalpy change to react these two to give this, should be exactly the same as enthalpy change of 1 plus 2, 3, 4, and 5. Okay, this is the Born-Haber cycle for the sodium chloride. Now let's talk about these 5 steps. So what do we have in the first step? This is sodium solid being converted into sodium gas. So we have enthalpy. This is the same as enthalpy change of sublimation. Enthalpy change of sublimation. Okay, this is solid changing into gas. And then here we have chlorine molecule being converted into chlorine atom. This is called enthalpy change of dissociation. Enthalpy change of dissociation. And then here we have sodium gas being converted into sodium ion, sodium atom to sodium ion. So this is enthalpy change of ionization energy, or the energy required to do this is the same as the first ionization energy of sodium. Here we have chlorine being changed into chlorine or chloride ion. This is the same as enthalpy change of first electron affinity for chlorine gas. And then this is the reaction of sodium gas, sodium ion gas, and chloride ion gas to give sodium chloride solid. Do you guys remember this? This is what we referred the lattice energy in minutes before in our discussion. So sodium ion plus chloride ion will give us sodium chloride solid. The energy required to do this is called lattice energy. So now, according to the Hess law, the energy required for the direct rods, which is enthalpy change of formation, should be the same as sum of all the energies in these 5 steps. Okay, it should be the same as enthalpy change of sublimation plus enthalpy change of dissociation plus enthalpy change of ionization energy plus enthalpy change of electron affinity and lattice energy. Now we can rearrange this to get our lattice energy, because all these values can be determined practically using experiments. The only thing that we cannot determine is lattice energy. That is why we're using this Born-Haber cycle. So let's rearrange. U is the same as enthalpy change of formation minus the sum of these enthalpy changes. Okay, so this is how we can calculate our lattice energy now. Now let's calculate the lattice energy of sodium chloride. Okay, I have written the values of all these enthalpy changes here. Let's use these numbers, or let's use this data to calculate the enthalpy change. I mean the lattice energy of sodium chloride. Okay, so the energy required to directly convert this and this into this is negative 411 kilojoules per mole, and all the other data are given here. So applying the Hess law, lattice energy is the same as enthalpy change of formation minus the sum of all the other enthalpy changes. Okay, enthalpy change in step 1 plus enthalpy change in step 2 plus enthalpy change in step 3 and enthalpy change in step 4. Okay, so our lattice energy will be now, what is enthalpy change of formation? It's given by minus 411 minus, what is enthalpy change in step 1? It's positive 108 plus in step 2, this is enthalpy change of dissociation for chlorine molecule. We have 2 chlorines here, but now we want enthalpy change of dissociation for 1 chlorine atom. So I have to divide this by 2. Okay, I'm going to take half of 240 plus enthalpy change in step 3 is positive 496 plus enthalpy change in step 4 is negative 349 minus 349. Okay, now lattice energy will be minus 786 kilojoules per mole. So this is how you determine lattice energy of any compounds. If you guys have comments, if you guys have questions, please don't forget or hesitate to write them in the comments below. See you in the next video. Thank you.